big goal of this chapter is to show you guys, or to teach you guys, how to write equilibrium expressions regardless of what your reactants and products are. And so we need to be able to write them regardless of if we have a heterogeneous or homogeneous reactions. What do I mean by that? By heterogeneous and homogeneous, I mean phases of the species. So far, I don't know if you've noticed or not, but so far I've only focused on systems that are all in the gas phase. They don't have to be in the gas phase. I could have aqueous, I could have liquid, or I could have solid. When you have things in different phases, that's called heterogeneous. They're not all in the same phase. When they're all in the same phase, it's homogeneous. Now, you do have to be aware of something though. If you remember, we've only done homogeneous so far. I've only talked about gas systems. In heterogeneous equilibria, not everything gets put into the expression. So far, I've written every reactant, every product into my K expression, or my equilibrium expression. But I don't always do that. If you have solids or liquids, we omit them from your K expression. But why? Well, the concentration, so, moles over liters of a solid or liquid, is an intensive property, and it doesn't actually depend on the amount of substance present. If I have less moles of something, it's going to take up less volume. So while we're looking at concentration for K expression, remember that is the concentration, it's not changing. If I have less number of them, it weighs less. It's going to take up less space. It's intrinsic. Concentration for gases and concentration for aqueous systems is not intrinsic and is always included in the K expression. But if you have a solid or a liquid, we ignore them. So again, like for density, if you have less of it, it takes up less volume. For molarity, if you have less of them, number of moles is the number of particles you have, the number of molecules, etc., it will take up less volume. So for equilibria occurring in aqueous solutions, we actually omit the water from the Kc expression. And in this case, why do we omit water? Because the concentration in water, although it is water, it is liquid phase, it's so large comparative to the species we're looking at that it's staying virtually constant. So if you see anything in the liquid phase or anything in the solid phase, you do not include them in your K expressions. You only include gas and aqueous. Let's work a few examples just to make sure that you guys are comfortable with this concept. So first thing you should do when you look at these, one of two ways to do it. Either look at these and say, okay, gas, I'm going to ignore the others. The other way to do this is to look at it and cross out. These are solid. I'm going to ignore them until you're comfortable with it. Your K expression is always products over reactants. So Kc, I'm going to first write down any products I have that are gas or aqueous. Again, I'm ignoring solid because the amount I have is staying constant for its intensive property, and I'm ignoring liquids. Concentration of CO2, and then I see that calcium carbonate is a solid phase and calcium oxide is solid phase, so I'm going to ignore it. The entire K expression for this is concentration of CO2. The equilibrium is only dependent upon the concentration of CO2. What about number 2? I've got Cn minus in the aqueous phase reacting with water to form HCN aqueous and OH minus. Kc, products over reactants. HCN is aqueous. I always include aqueous. So concentration of the HCN, or hydrocyanic acid. OH minus, or hydroxide. My concentration of hydroxide, it is aqueous. Divided by my cyanide, Cn minus. And then H2O is omitted because it is virtually constant. Magnesium oxide reacting with CO2 gas to form magnesium carbonate solid. Kc. In my numerator, I'm going to put my products, except the only product I have is magnesium carbonate in solid phase. I do not include solids in my K expression. So I'm going to put a 1 in my numerator. I can actually do, so it looks like a 1. And then I'm going to look at my my reactants from the denominator. Magnesium oxide's a solid, so I ignore that. And CO2 is a gas. So my entire K expression is 1 divided by the concentration of CO2. And lastly, 2 moles of water, liquid, in equilibrium with H3O plus and OH minus. Notice that your hydronium ion is aqueous. Hydroxide ion is also aqueous. So your Kc expression here will be the concentration of your hydronium ion times the concentration of your hydroxide ion. I have water in liquid phase, and because it's in a liquid, it's staying virtually constant throughout the entire reaction, so I ignore it and I do not put it in my K expression, and this is also complete. Make sure you are comfortable writing K expressions, whether they be homogeneous or heterogeneous reactions. One thing I forgot to mention at the very end here when I ended the last video was this expression here, where I wrote Kc is equal to H3O plus times OH minus. It's actually a very special case that you're going to learn about and use a lot in the next chapter. But this has a very specific value. It's actually equal to 1.0 times 10 to the negative 14 at 25 degrees C. So this, something that's going to come back. It's called your KW. KW because water. It's your K expression for water. We're going to use it a lot in your acid-base chapter, though. So that one's coming back in the next couple chapters, but it's a very special case. It is a Kc expression, yes, but it's actually equal to Kw. So instead of Kc, we can actually write Kw here, and this is your Kw expression. Kw is equal to the hydronium concentration times the hydroxide concentration of your system, and that always equals 1.0 times 10 to the negative 14 at 25 degrees C. And if you remember learning about acids and bases in the pH scale, the pH scale runs from 1 to 14. It's based on the 14 right here.